Okay, the last speaker of today will be Yuchen Liu from Northwestern University, and he will talk about the ACC for the local volumes and the boundaries of singularities.
All right, thank you very much for the invitation. The introduction and the great things speaking in honor of the Professor Dr. 72 birthday, which is a very good library in Chinese culture. Doesn't be divisible by 12. So you know Chinese study.
Yeah, 60.
It is a period of 12. Okay, so I want to talk about something about singularities. So this is like a new invariant compared to NLD. Right, which Professor talked about. So this is going work with Jingjun time. And so let me just remind you the definition of chaotic singularity. So whenever we always work over complex numbers. And then chaotic singularity is pretty much just so I start from points on some normal variety x, and then together with a q divided delta or r divided. So let's say x is normal, and then delta. And then we have kx plus delta k. And then my x, delta x is close point. Then we define KLG by looking at the so-called log discrepancy of divisors. So I think this has been done many times today. It's pretty different from usually where I give a talk where not too many people are familiar with this, but I guess this part is really good. So I will do it fast. So we take any resolution, and then so let's say this is directional. And we will assume x goes to normal. And then this E is a time divisor inside x tilde. And then you define this log discrepancy. Which I use this capital A notation, sometimes denoted by little a. So we use this delta. So 1 plus the coefficient k x tilde minus the, let's say this that is sigma and minus sigma other. All right, and then we say this singularity is KLC. That's for Kawamata of capital. If is positive, E over x. By saying divisor over, right? I just say divisor on some directional order, like this x tilde. And then we say this is log canonical. If the same thing holds except the pure log dispersion and negative. All right, so these are some standard definitions, and to define the minimal log discrepancy, of course, you just take the infimum over this log discrepancy for every divisor, maybe exceptional divisors or divisor centered at a certain point, or maybe I should say, okay, sometimes I will restrict the divisor center at that close point. And then to define the local volume, you need a little bit more. So because MLD, we know that it is computed in log resolution. So it's a invariant that can be computed by finite, taking minimum of finite many numbers. But then for the local volume, first of all, you need the volume. Normalize volume divisor to the evaluation for in general evaluations, and then you need to take infimum over all divisors. And unfortunately, sometimes there are no divisor minimized. the invariant. Right? So then we define the volume. So suppose, let's say E is a divisor over X centered at this point. So this just means that the sigma of E equals this 0.x. All right, and then we define volume of E. So this is defined as some kind of multiplicity of the ideals induced by E. Okay, so I will give this definition first and then explain some cases where it appears in other forms. So what you do is you look at the length, or maybe I should write this dimension over C. So you have the local ring of your variety at this close point, which is a localization of some finite energy given C. And then you take portion of this ideal, which consists of all the functions, such that the order of vanishing of this function along E is at least m. So m is some integer that grows. All right, so this is a function in the integer m, and it grows like a polynomial of degree n, where n here is a dimension. And then we take the ratio. Pretty much we want to take the leading term of this polynomial and normalize that is the factorial. So here n is an. Okay, so this is the invariant that come from looking at sections of line models managing to some order at this divisor, and then there's some something we can do. So this is for volume. Something we can do with this two invariant is this so-called normalized. So this is first pinned down by Yuchen Liu. So the definition is very simple somehow. You have this two invariant, and what you do is you just multiply them in the following way. So we define this normalized volume, which is notation is this volume patch of E. With respect to this pair, I guess there are three sub-notations, but sometimes I will just drop them. I just mean to take the normalized volume of the divisor at the singularity. To be, you take your log discrepancy, and then you raise to the power n, and then you multiply the volume. Okay, so the reason why we take the power n to log discrepancy on the other powers, for instance, naively, you may just want to take multiplication of this quantity, is that we want this invariant to extend to valuations in a nice way, such that it becomes a rescaling invariant. Okay, so similar to NLP, where we always want to minimize something, here we also want to minimize this normalized volume, and that's how we define this local volume. But unfortunately, we can only take infinite. We define the local volume of the singularity to be the infinite of this normalized volume of all divisors. So here E is taken by all divisors over X centered at this zero. Okay, so that's our definition. And let's just try to give some examples to motivate how this invariant really looks like. All right. So some examples. First of all, let's just look at the smooth point, right? So we take actually a n, and this is actually the origin and delta. Let's say this is 0. Okay, so take the simplest case. And then the first divisor over the origin of a smooth variety or any smooth point on a variety is to take ordinary. Okay, so then let's say E is the ordinary exceptional divisor of the ordinary blow-up, so blow-up of 0 AM, that's 2 AM. So then this is very simple to compute where the block discrepancy is just a dimension. And then the volume is also relatively easy to see. So pretty much I'm just looking at the data. Okay, so I guess it's blocked by the projector, but it's a okay. The ring is you take the local ring at this point and then you function out that maximal ideal to the nth power. Because here, if you remember this ideal F where order E is at 1 is exactly the same as the maximum ideal for power. Okay, in this case. So therefore, the volume turns out to be 1. Okay, and then you multiply them and get this normalized volume is 10. Okay, so this is a quite naive kind of example, but turns out that this is a minimizer. So here due to definitely I missed that. And should be. So what they show is in the definition you have to take infimum over all divisors, and you know even for the case of A2 there are so many blowups or sequence of blowups. So infinite many families of hexagonal divisors, and then at the end you take infimum, turns out this is your minimizer. Any smooth point, well, I guess it's definitely because it's like formal invariant. So this holds for any smooth point too. But turns out this is minimized at this elevation. So actually, an interesting consequence of this theorem, or let's say a baby version of this theorem, is the so-called AMG inequality. So what's going on is if we just take E be a weighted blow-up, it's like an exceptional of a weighted blow-up. Let's say of weight equals A1 up to A. Here, this weight of the integers. And then you can assume they're co-prime. Then what's going on is non-determinacy. Okay, so I guess I should label this. Then the non-determinacy is just the sum of the exponents. And then the volume is the product of this then you invert it. So then you see that in this case, normalized volume is exactly the sum of x power divided by the product. And we're just saying it's bigger than or equal to, which is data next year. Okay, so that gives you some kind of feeling of this invariant. Any questions?
Well, Henry, can you calculate the resolution?
You mean can you reach the infimum on some resolution? No. So the answer is okay. Maybe I should say it now. So this is the remark. So the infimum. Okay. So what we define is local volume. So this is the definition is the infimum of all vectors, right? So the infimum may not be. Okay, so actually an example can be given something like this. Just take half the tone over your blow up of E2 at the point. And take that into number. And you compute, so this is a toric example, there's a way to compute all the toric volumes, or toric singularities, and you compute it, some convex geometry tells you this is actually irrational. Okay? So some kind of algebra integer of order 2 over Q. So it's not really achieved by any device. So that sort of is a bad news somehow for us, because we know MLT or LCT are always computed by some divisor. So therefore, we sort of tell us that we should enlarge our space. As you saw in that example, it makes perfect sense to say we can grow with irrational coefficients as long as we trigger mass evaluation. So then that definition should extend, right? Because the definition are like polynomials in the exponents. Even if they are real numbers, it would make sense. And the inequality makes sense. And what's more interesting, you can see these two invariants, AX and volume, are all continuous on the exponent. So it should make sense to extend it. And that's the way, I guess, Shirley did. And then after SMA and Skata, sorry, should be Johnson and Skata, and I and others Smith. So pretty much he introduced this normalized volume of evaluation. So here V is just an evaluation of the function field CX centered at this point. And then you just define similarly. There's a way to extend the valuation. The log discrepancy makes sense for valuations just by approaching the valuation using a sequence of divisorial valuations, so order of EI, and after some rescale. And this is homogeneous to one. And then multiply the volume of the valuation, which makes sense even in that original definition. So then it is proved by Harold Bloom that there exists a minimizer. There is a minimizer valuation of this functional. So therefore, in this definition, okay, so in this definition, it's defined for simplicity to run over all valuations, but actually, you can also define all valuations B that are not necessarily divisorial, and turns out there exists a minimizer. And then we know more, so it is worked by Jingjun that this minimizer is actually possible. So quasi-monomial is pretty much like a weighted blow-up valuation with the AI being possibly irrational, but on some higher model, on some resolution. Okay, and we also know something that's stronger, so we should prove that the minimizer is unique up to some discrete. So pretty much this gives us a canonical object to the singularity. And the idea of this whole, the idea behind this whole definition is this valuation should give us some kind of stable degeneration. Okay. All right. So let me move to this question today that we want to consider boundedness of singularities. So let me give one more example of multi-limit. So the good thing about this volume is it really behaves like what we know, regular geometry, the volume of a Riemannian manifold. So for Riemannian manifold, if you have a cover, right, then you imagine that the covering should have volume equals to the volume of the base times the degree of the map. And this is exactly the case. And in particular, we have this. Okay, so this is a simpler version of that. But if you take a finite group and take a quotient of AN by this finite group, then this volume is exactly the volume of the smooth point, which is n to n divided by the order of. Okay, so this already tells you some difference of the local volume compared with MLT, because say we look at A equal 2, and then we look at all the wall singularities, like AN type singularities. Then your group G grows, right? So your volume somehow goes to 0 when n goes to infinity, but they are canonical, so their MLT equals 1. And actually there is a comparison. So this is a work by we show that there is a comparison where the local volume is always smaller or equal to, I guess, MLT smaller than MLT of the singularity, and then divided again by this. So somehow requiring the local volume has a lower bound is a stronger condition than MLT. Okay. All right. So from this example, you kind of see that if I have a lower bound on the local volume, then the group G here is bounded above. So that implies there are finite in any type of similarities. And actually, you're right. Yes. Okay, thank you. Yeah, but again, you see this is not sharp. As if you take smooth point, here you get n to the n, here you get n to the n plus 1. So an interesting question is to find the sharp. Anyway. Yeah, so therefore the general expectation that if I have a lower bound, positive lower bound on the local volume, then the singularity are bounded. Yeah. So as you can see that this works pretty well for 2 dimensions without say delta equals 0, because in 2 dimensions KLT singularities are both they're the same. So therefore this is automatically. But unfortunately in dimension 3, this is not the naive version of boundedness does not work, as we have some more examples. And this sort of again, this example will lead us to the way to guess what should be the correct picture. So these examples are also kind of famous. They are the 3-dimensional AK singularities. So they're just given by x squared plus y squared plus b squared. Then I just take the word. And there's no, okay, so this is my xk, and there's no delta. So then in this case, turns out we separate into 3 subcases. So first of all, if k equals 1, you end it up in the original W point. So then the volume is 16 is computed by the usual law, k equals 1. And then for k equals 2, that's a natural choice of valuation, which is make this homogeneous. And that price a minimizer. So it turns out you get a slightly less number. And then for k equal to 3, you get the same, 27 over 2. And there's a reason why this number show up, because 27 is 3 cubed, right? So that's the volume of smooth point in dimension 3. And you're dividing 2, that sort of indicates that you are doing some kind of motion. And that's exactly the case where I have x in infinity. It's just x squared plus 0 inside form. And this is exactly the 2-dimensional A1 singularity across a line. So that's a 3-dimensional singularity of order 2. And you see that this is exactly induced by the minimizer of this all this B star. Two conjectures. So the first conjecture concerns the question about the distribution of this volume. So you can imagine that in a bounded family of singularities, we know that the MLB are their constructive function. So they're only finite many values. And then you imagine similar thing is true for normalized volume, and this is true for Young. So therefore boundedness should have some implication for the distribution of these values, and these are like ACC type things. So this is, let's say we have coefficient set I, and then is the dimension of X, and then we define this set of local volumes. All such singularities such that the delta has coefficient inside I. Okay, so then the conjecture is then, first of all, if I have I is finite, so if I have a finite coefficient then this set is discrete away from 0. So this should mean that the 0 is potentially the only accumulation. And second, if I satisfies ACC, then this set satisfies ACC. All right, so this is closely related to the second conjecture, which concerns the boundedness question, and maybe I won't have time to. Let's see, do I have time? Okay, so perhaps I should state it slightly differently. So conjecture 2 says the following class of singularities, classes of singularities are equivalent. Okay, so the first class is, again, I just take the singularities of dimension n. So I will probably avoid, let's say, fixed dimension n. And then here the assumption is just a local volume of the singularity as a lower bound. Positive. And then the second set are the singularities that admits so-called delta and LB has a lower bound. So this equivalent it should be interpreted the following way: for every this class is contained in some delta and eta, and vice versa. For every eta and delta, there exists some the background. Okay, so the second condition, I guess I didn't explain this part. So delta PLT blow up, you can think about this as saying more or less that there exists a so-called PLT blow up that extracts a Kawamata component, which is a long funnel variety of one-dimensional roller, and that long funnel pair is delta KL. Okay, so we know that by BAB conjecture, this implies that these exceptional divisors are bounded, and this condition sort of bounded. Okay. Yeah, so let me say the main result, and then I take some remarks and see if I have time for some proof. Okay. So theorem one, is that conjecture one is true if you assume some conditions on either dimension or some family of the singularity. So the first situation is where my singularity, if I forget about the delta, I just look at the terms, and I assume they belong to is still going side, and belongs to bounded. So here I can put a little bit analytically on it. Okay, so here this family should be considered part of the data. For example, you can think about X to be a smooth point. So that's like analytic boundary. Very special example of that. Okay. Yeah, so in other words, we proved this ACC for local volume conjecture if you are in the smooth structures. And 2 is when n equals 2, so 2 dimensions. Where pretty much you can see that it will follow from 1 because in dimension 2, your ambient germ is the quotient singularity. And then that example tells us that the group should be bounded once your local one is the lower bound, so that it reduces. And 3 is when n equals 3, x is terminal, and delta is. Okay, so somehow for terminal threefold singularities, there's a way to reduce to the bounded germ. So that's what we do. All right, and then of course theorem 2 is the answer. So conjecture 2 means exactly the same. Yeah, maybe I should write it here. So theorem 2 says the same. So conjecture 2 holds in 1 to 3. And I guess there's one direction that we can show conjecture 2. So conjecture 2 should have 2 directions. And the typical direction is from the lower bound of the local volume to get some kind of boundedness. Because you can think about this condition is more or less boundedness. So what we show is the bounded implied lower bound of local volume is also. So somehow the hard condition, the hard direction of conjecture 2, we only verify in this case.
Yeah. So this conjecture 2 says that if the normalized volume is bounded away from 0, then you're bounded up to information, right?
Yes.
So
yes.
if you say, let's say, normalized volume bundle with zero and some sort of p stable scale of these singularities, do you actually get a proper bundle?
Yeah, that's a good question. I don't think we know that. Even if you consider three-dimensional. Well, maybe three-dimensional, there's a result that I will mention. But other than that, we don't think that we know. Even if you assume there exists a stable generation. So it's not a consequence of stable. Okay, any other questions? Yeah, let me make a remark of the things that happened before or after our work. So first of all, I mentioned this condition, bounded-plt blow-up, and the existence of that together with the lower bound of the MLT. So in a work by Jingjun and Yuchen Liu and Kawamata, so they show that this condition of existence of delta plt blow-up plus MLT is bigger than beta bigger than 0. So this implies that the singularities are bounded up to so-called spectral generation. So this special degeneration is something arises from the study of case stability, where you have a family of varieties over A1, and then there's a C-star action on A1 that leads to C-star action on X. So pretty much all the fibers are the same except the central fiber. And then there's a section. Maybe I shouldn't use sigma, but let's use tau. So there's a section of this family that gives you a family of singularities. So it may look something like this. You have a singularity which is pretty non-regular, and then maybe in the deformation, so this is xt, which is x, and this is x. So what they say is with this condition of x, then you can get a bounded family of these cones. And this is, I guess, mostly, their work is mostly based on the okay, so this explains that why we want this condition to be true, because it implies boundedness after degeneration. As you saw in that three-dimensional AK singularity example, they are not bounded because K can be arbitrarily large, but they all degenerate to this infinity singularity. And that's okay, and some other developments after our paper was so this is one, and another is the work of Kawamata and Tooth. And I think independently by China as well. So they confirm conjecture 1 and 2 in Fourier case. For Fourier. Right? Maybe your work didn't consider the case of devices. I guess the transfer. And lastly, a recent work of today, I think we will talk about this in this talk. So he showed that conjecture 2 holds in dimension 3 as well. So our example, our statement for dimension 3 is not complete because we only treat the terminal case where divisor is 0. But Zuchai found a really nice argument to handle the whole case. All right, so these are the statements, and hopefully, this result could imply conjecture 1 also true in dimension 3. But I don't have a certain answer. Be interesting. This integration. Okay, any questions? All right, so I have like about 7 minutes. So let me briefly explain the idea. I'll mostly focus on theorem 1, and actually maybe I only have time to cover the first case where your ambient germ is bounded. And the statement is if you have a bounded ambient germ, then you should expect that your local volume satisfies some either discreteness or the ACC condition, depending on the coefficient set. Yeah, I guess that erase nothing back to one. Yeah, okay. So anyway, so we assume this this condition of bounded term. Let's say so the assumption is this bounded. So then the new thing is if delta also bounded, and we have a result by JAMI that the local volume is finite. Okay, here I'm assuming, let's say multiplication I is finite. Right, so therefore, Chang's result will just imply what we have, right? At least in the finite coefficient section. But the problem is delta may not be bounded. As you can see again from a very easy example. Let's see.
What do you mean by bounded? Find communication.
Maybe I should say support. Yeah.
Support. Support is not.
Yeah, support.
Not cache.
Not bounded. So there's an easy example that shows that what happens if you have unbounded right. So here I'm just taking like a cusp, right? It's appearing so you have a cusp, which I'll put it to 2m. And then I guess m equals 3, then ordinary cusp, m can go large. And then this singularity is actually encoded by this singularity x square plus I guess that will be z square here. The Platon quotient, right? Where this cuspidal curve is exactly the ramified limits. Okay, and because we know local volume are multiplicative, so therefore this singularity, if we compute its local volume, then that's 1/2 of this local volume here. So you put the x m. This is very easy to compute. It's just 4/1/2. That goes to 0. Okay, so then as you see that if your curve or divisor is not bounded, then it takes some effort to bound those. So our goal will be if this number has a positive lower bound, then this m should, it cannot like go to infinity. And what we can do is we take a truncation of the divisor. So there are 2 steps. So step 1 will be take this truncation. So we write down the K to be the case of delta. So by truncation, I just mean you look at the equation defining delta, and then you just throw away all the powers in the Taylor expansion whose power is bigger than k. Okay. So that then you get you create something bound, right? But you saw in that example, if I just done k, but let n go very large, then you sort of get a different singularity where the local volume difference, and that's something we don't want. So therefore, we show that if there's an invariant that controls this k. So if the local threshold -1 of this singularity is bigger than some constant gamma. So imagine in that example, you have local threshold exactly so 2 times 1/2 plus 1 to the n minus 1. And this is like also 2 over n. And that goes to 0. So therefore, this condition is to ensure that you're not ending up in that limiting 0 case. All right. So if this is true for some constant gamma, then we can find a k depending on this constant, such that the truncation does not change. So this is pretty much estimating what happens for the minimizing valuation. Because the valuation stays are the same, and then you just compare their normalized volume, and if they differ, we show that it cannot be minimized. All right, and the second step is to show that this condition can be implied by assuming normalized volume having a lower bound. So what we show is there exists some positive constant depending on some coefficient set, such that we have a inequality where C times is somewhere from above. Okay, so therefore, if you assume this is bigger than epsilon, then this will be bigger than C times epsilon, and then this will be back down in that. Okay, so the last remark I want to make is recently to try to improve our graph. So he can show that the C can be chosen only depending on dimension. Okay, so I guess I will stop here. Thank you.
Let's speak again.